Imagine a world where ambulances soar through the sky, their sirens replaced by the quiet hum of anti-gravity drives. Picture microscopic robots, smaller than a speck of dust, assembling complex structures with impossible precision. This is the 22nd century, where the line between science fiction and reality blurs. The skyline glows with the adaptive brilliance of buildings that seem to breathe, each one connected to a vast network of knowledge and energy. Remember when a helmet was just a hard shell meant to protect your head? In the 22nd century, helmets have evolved into something far more extraordinary. Woven into the very fabric of these helmets are neural compute threads, so thin they feel like a second skin. But don't let their delicate nature fool you. These threads are constantly at work, monitoring your every thought, your every stress signal. These aren't just helmets, they are sentient companions. They read your brainwaves, analyze your micro-muscle tensions, and assess your cognitive load in real time. But here's the truly amazing part. These helmets can predict accidents before they even happen. Quantum-enabled predictive modeling analyzes trillions of data points from past rides, factoring in everything from road conditions to rider behavior. This data, combined with the real-time neural feedback from the helmet, allows the helmet to simulate thousands of possible crash scenarios every millisecond. When an accident is imminent, the helmet doesn't just send an alert, it takes action. Using charged graphene woven into its structure, the helmet triggers magnetic field shields around the rider's body, creating a protective bubble that can deflect even the most catastrophic impacts. And where are these life-saving journeys taking place? Not on the GPS-mapped roads of the past, but on the quantum highways of the future. QPS, or Quantum Positioning System, offers accuracy down to the atomic level. No more getting lost in concrete jungles or signal-blocking tunnels. QPS guides you with unwavering precision. Let's travel to 22nd century Mumbai. Our protagonist is a courier, navigating the Hyperloop bike routes at breakneck speed. His AI-linked helmet detects a spike in his stress pattern, a subtle tremor in his hand betraying his anxiety. Before the courier even registers the danger, the helmet takes control, slowing the bike autonomously and broadcasting an alert to the entire fleet. A chain collision, a tragedy waiting to happen, is averted in the blink of an eye. Now let's rewind the clock back to 2025. A lone rider in Delhi navigates pothole-ridden roads, his trusty helmet strapped firmly in place. But this helmet can only react, not predict. When a hidden pothole sends the rider flying, the helmet can only do so much. The difference between these two scenarios? The difference between life and death? In the 22nd century, machines have become more than just tools. They've evolved into self-aware entities, capable of monitoring their own health with a level of detail we could only dream of in the past. Embedded within these machines are quantum thermal lattices, or QTLs, microscopic networks of entangled particles that act as hypersensitive thermometers. Imagine a sensor so precise that it can detect temperature fluctuations at the atomic level. That's the power of QTLs. They can sense the slightest hint of thermal stress, a feat far beyond the capabilities of even our most advanced sensors today. But QTLs don't just monitor, they communicate. These lattices are in constant contact with a central quantum AI supervisor, a silent guardian that oversees the well-being of entire factories. The supervisor uses multidimensional data modeling to analyze the information streaming in from the QTLs, forecasting potential thermal stress and wear out months in advance. This isn't just preventative maintenance, it's preemptive action. Instead of waiting for a machine to overheat, the system automatically adjusts thermal gradients, rerouting internal coolant plasmas or opening adaptive nano-venting pores. It's like having a team of microscopic mechanics constantly fine-tuning every aspect of the machine's operation. To truly appreciate this leap in technology, let's compare it to our current methods. Today, we rely on sensors like the DHT11 or DS18B20 to monitor temperature. These sensors are connected to microcontrollers like the ESP8266, which then send data to a cloud dashboard. While this system can trigger alerts if temperatures exceed preset thresholds, it's a reactive approach, not a proactive one. Maintenance decisions are based on fixed rules and historical data, not on real-time forecasts and the unique needs of each machine. Let's take a trip to a bottling plant in Bengaluru, both in the year 2025 and in the 22nd century. In 2025, the factory grinds to a halt as a critical piece of machinery overheats. The air fills with the smell of burnt oil and the frustrated shouts of workers. Now, fast forward to the 22nd century. The same factory, now equipped with QTLs and a quantum AI supervisor, hums with quiet efficiency. Chapter 3. The Quantum Choreographer's Material Handling in the Age of Instantaneous Communication. Imagine a world where factories are no longer bound by the limitations of physical conveyors and pre-programmed robots. In the 22nd century, material handling has been revolutionized by the power of quantum computing. At the heart of this revolution lies the Quantum Logic PLC, a device that makes even our most advanced PLCs look like clunky calculators. These aren't just programmable logic controllers, they are the brains of the operation, capable of understanding context and adapting to changing circumstances. Each Quantum Logic PLC is linked to a vast quantum mesh network, allowing it to communicate instantaneously with every other machine in the factory and even across global plants. But the true magic lies in the AI dust, microscopic sensors that attach to every object in the factory. These aren't just RFID tags tracking location. They provide a constant stream of data about the object's state, stress level, and even its destination urgency. Imagine a ballet where every dancer knows exactly where to be at any given moment, adjusting their movements in perfect harmony with the others. That's the level of coordination and efficiency we're talking about. Let's contrast this with the material handling systems of today. We rely on PLCs from companies like Siemens and Allen Bradley, using ladder logic to control the flow of materials. While HMI screens and sensors provide some level of feedback, the system is inherently limited in its adaptability. Integration with SCADA and MES systems is often hampered by protocol compatibility issues and network stability problems. The result is a system that's efficient but inflexible, prone to bottlenecks and disruptions. Let's travel to a bustling factory in Pune, both in the year 2025 and in the 22nd century. In 2025, a jammed conveyor belt brings the entire production line to a screeching halt. Workers scramble to identify the problem, precious minutes ticking by as the backlog grows. Now, fast forward to the 22nd century. The same factory, now overseen by quantum logic PLCs and AI dust, hums with quiet efficiency. Chapter 4. The Quantum Mirror, Predicting and Preventing Failures Before They Occur. In the world of 22nd century manufacturing, the phrase unscheduled downtime has become as archaic as dial-up internet. Machines no longer break down unexpectedly. They are constantly monitored and maintained by a network of quantum sensors and AI so sophisticated that it borders on the supernatural. At the heart of this system lies the concept of the quantum twin, a real-time, entangled simulation of each machine that exists in the quantum realm. Every vibration, every temperature fluctuation, every infinitesimal change in the physical machine is mirrored in its quantum twin. But this isn't just about monitoring, it's about understanding. These quantum twins are analyzed using quantum harmonic spectrometry, a technology that allows us to listen to the music of the machines at a subatomic level. Imagine being able to hear the faintest dissonance in an orchestra, a single note slightly out of tune, and knowing exactly which instrument was causing the problem. That's the power of quantum harmonic spectrometry. This technology allows us to detect anomalies weeks, sometimes even months, before they manifest in the physical world. And once a potential fault is identified, the system doesn't just sound an alarm, it takes action. Machines in the 22nd century are built with self-healing polymers, materials that can repair microscopic damage at a molecular level. These polymers are activated by the quantum system, flowing to the site of the potential fault and reinforcing the material before any significant wear and tear can occur. Compare this to our current methods of fault detection. We attach piezoelectric sensors and accelerometers to our machines, analyzing the data using FFT algorithms and machine learning. While this can help us identify some problems, it's a blunt instrument compared to the scalpel-like precision of quantum harmonic spectrometry. Let's take a look at a wind turbine farm in Tamil Nadu, both in the year 2025 and in the 22nd century. In 2025, a turbine begins to vibrate unexpectedly. The control room lights up with alarms, but before engineers can pinpoint the problem, the turbine shuts down, its massive blades grinding to a halt. Now, fast forward to the 22nd century. The same wind farm, now equipped with quantum twins and quantum harmonic spectrometry, hums with quiet efficiency. The factory of the 22nd century is a symphony of synchronized motion, a testament to the power of mechatronics taken to its ultimate evolution. There's no panic, no frantic scrambling to fix unexpected breakdowns. Everything hums with a quiet confidence, a sense of purpose that permeates every corner of the factory floor. Helmets predict accidents before they happen, machines heal themselves before damage can occur, and entire factories move with a ballet-like precision orchestrated by invisible quantum hands. The machines of the 22nd century don't just work, they think, they adapt, they evolve.